Welcome to class 13, class activities. We're supposed to be graphing square root of x by hand. You can do that by making a table of values. So we do x and f of x. I'm going to carefully choose my x values so that I can easily take the square root of them. So I will do 0. I can take the square root of 0. I can take the square root of 1. It's 1. And then I'm only going to list perfect squares here so that I can easily take the square root of them. And based on my axis, the last x value that's easy to square root is 9. The next one would be 16, and that's off the x-axis. So I'll stop at 9. So I have 0, 1, 2, 3 are my y values. So I'm going to go 0, 0, 1, 1, 4, 2, and 9, 3. Connect them with a nice smooth curve. And that's the graph of f of x equals the square root of x. Now I'm going to graph g of x and h of x, the square root of x plus 2 and the square root of x minus 5 using some technology. But before I do that, let's see if we can predict based on the demo, what happened in the demo, what's going to happen to these graphs compared to f. So g of x is the square root of x plus 2. So I'm going to predict based on what happened in the demo that this is going to go up 2. And h of x is the square root of x minus 5, and that this is going to shift down 5. All right, so I'm just going to do these two graphs using some technology. So I have f already graphed here, and then g and h. And yeah, it looks like g took f and went up 2, and h started at f and went down 5. So I will take a quick picture. Okay, I pasted the picture from GeoGebra into our file here. There. Okay, so again, we're going to describe how the original graph of f has been transformed to get each of the new graphs. And it was exactly what we predicted. To get the graph of g of x, the graph of f of x shifts up 2. And to get h of x, the graph of f of x shifts down 2. To verify that that's really what's happening, I'm just going to check a couple of x values and make sure that f, g, and h have the appropriate relationship. So f of 0, remember f of x is the square root of x, so f of 0 is 0. G of 0, if I put a 0 in for g, I get the square root of 0 plus 2, which is 2. And if I put a 0 in for the x's in the h function, I get 0 minus 5 is negative 5. And so I do have the appropriate relationship between f and g, right? My output of 0 becomes an output of 2. And then f and h have the appropriate relationship because 0 minus 5 is minus 5. One more x value to check, I'm going to do 4. So f of 4, that's the square root of 4, which is 2. G of 4 is the square root of 4 plus 2, so that's 4. And h of 4 is the square root of 4 minus 5, which is 2 minus 5 minus 3. So let's make sure these have the correct relationship. So f and g, you're supposed to be adding 2. The y value should be related by adding 2 to f. And so 2 plus 2 is 4. And f and h are related in that you should be subtracting 5. So 2 minus 5 is negative 3. And I didn't ask you to find f of negative 4 because f of negative 4 would be the square root of negative 4, which when we're graphing is undefined, right? It's actually 2i, but there's no I axis. These are both real axes in this case. All right, we want to rewrite g and h as transformations of f of x. So g of x, if you remember, we defined it as the square root of x plus 2, but the square root of x is the formula for f of x, so we would write this as f of x plus 2. And h of x, that was the square root of x minus 5, so we could rewrite that as f of x minus 5. And I'm going to apply the transformation to a few points to find the corresponding points on the transformed function. So I'm going to use the points that I originally plotted when I did this by hand. I had 0, 0, 1, 1, 4, 2, and 9, 3. And I'll do one more. I'll do 16, 4. Those are all points on the f of x equals the square root of x. To get the corresponding point on G, you just have to add 2 to the y value. So I have 0, 2, 1, 3, 4, 4, 9, 5, and 16, 6. Okay, so now I'm going to graph square root of x again, and then I'm going to graph 2 more transformations of square root of x. I'm going to do all of this in GeoGebra. You would have done the first part by hand, but I'm going to graph all of these in GeoGebra. Okay, I used GeoGebra to graph the 3 functions they asked about. Green is f of x, the square root of x. Red is g of x, which is the square root of x minus 3. And blue is h of x, the square root of x plus 2. So in our own words, we want to describe what happened to the original graph. All right, so to get from F to G, if I just look at the starting point, right? F starts here and G starts here. It looks like what happened is the graph shifted to the right 3. And is that actually what happened? Let's check a few more points, right? So let's look at another point on F, this 1, 1. The next nice integer point on G is at 4, 1. So from 1 to 4 is 3 units to the right. I'm going to check one more. Let's see, I have 4, 2. That was one of my points on G. Corresponding point on, it's one of my points on F. Corresponding point on G would be right here, which is 3 units away. So it looks like I have a consistent distance of 3 units for corresponding points on between F and G. All right, so G, the graph of F shifts 3 to the right. That might be surprising, right? You might think that that minus 3 would mean you move left 3, but it turned out we moved right. It's an interesting thing to consider. We'll think about it in a minute. For H, let's see, we'll plot some corresponding points on F and H. So F starts here at 0, 0. H starts here at negative 2, 0. That is a distance of 2 units. Here's my another point on F, 1, 1. The corresponding point on H is right here, a distance of 2 units. Moved left 2 units. And then here's my next one on F. The corresponding point on H is right here, 2 units to the left. So it looks like to get the graph of H, the graph of f of x shifts 2 to the left. So what besides the direction is different about the way this transformation changes the graph from what we did in the demo? It's the minus sign, right? In the demo, negative meant down and positive meant up. And things were moving vertically, right? So now my minus signs are underneath the square root instead of outside. And that means we move horizontally, left and right. And the minus meant right and the plus meant left. All right, so I want to verify what I discovered here. So f of 0, remember f of x is the square root of x. So f of 0 is 0. G of 0, that's the square root of x minus 3. Oh, I'm sorry, I'm not doing g of 0, I'm doing g of 3. So g of 3, remember g of x is the square root of x minus 3. So if I put a 3 in for x, this is actually the square root of 0, which is 0. And then h of x, that is the square root of x plus 2. So h of negative 2, if I put a negative 2 in for x, negative 2 plus 2 is 0. The square root of 0 is 0. So what I'm trying to show here is that in order to get the same y value, in order to get the 0, for f and g, f you can plug in a 0, but for g, you can't put in a 0 because you get the square root of a negative. In order to get the 0 as the output, you would have to put in a 3 for x, which moves the whole graph to the right instead of to the left. And then for h, to get a 0 as the output, you'd have to put in a negative 2 for x, and that moves the whole graph to the left. All right, let's check one more set of y values and make sure that the x values have the appropriate relationship. So f of x is the square root of x, so this f of 4 would be 2. G of 7, so here's my g of x. If I replace this x with a 7, 7 minus 3 is 4, square root of 4 is 2. And then h of 2, I'm going to put in a 2 for my x into the h formula. That ends up giving me the square root of 4, which is 2. So to get the y value of 2, in f you plug in a 4, in g you plug in a 7, and in h you plug in a 2. And these x values have the relationship of shifting the way we described, right? 4, you move right 3 and you get to 7. And from 4, you move left 2 and you get the 2. So it's a little bit counterintuitive when you first see it, but then once you think about it in terms of how do I get the same output, the direction move starts to make a little more sense. All right, so I want to rewrite g and h as transformations of f. So let's just remember that g of x is the square root of x minus 3, and h of x is the square root of x plus 2. So I want to rewrite g in terms of f. So before I was doing f of x and then plus or minus a number. But now what's happening is you're changing the x value. So this is going to be f of x minus 3. So I have to change the x so that that minus 3 will go under the square root. I need to put it in the parentheses. Same for the h of x. So h of x is f of x plus 2. So I'm going to apply the transformation to a few points on f, find the corresponding points in the transformed function g. So pick some points on f. I've got 0, 0, 1, 1, because f is the square root of x. So I have 4, 2, 9, 3, and 16, 4. So for g, that's f of x minus 3. So we decided that that means a transformation that's going to move everything to the right 3 units. The way you cause a movement to the right by 3, you'd have to add 3 to the x value. So corresponding points after the transformation, add 3 to every x value. So I get 3, 0, 4, 1, 7, 2, 12, 3, and 19, 4. Okay, I'm going to practice identifying parent functions here. So here the underlying parent function is going to be x squared, and then you can talk about transformations. That plus 2 that's on the inside would mean you move left 2, and the minus 5 that's on the outside would move down 5. Okay. If you look at the next function, it looks very similar, except what we're transforming is x cubed. Right, you would start with x cubed and then move it left 2 and down 5. If g of x were the square root of x plus 2 minus 5, the function we'd be transforming is the square root of x, and we would move it left 2 and then down 5. And if g were just plain old x minus 5, then the parent function f of x is just x, and you shift it down 5. All right, to summarize, we have learned in this lesson about horizontal and vertical shifts. So if f of x is our basic graph or our parent function, c is a positive real number, then g of x equals f of x plus c is the graph of f of x shifted c units upwards. F of x minus c is the graph of f of x shifted c units downwards. And f of quantity x plus c is the graph of f of x shifted c units. Oops, I wrote this backwards. We're shifting by c units leftwards. And f of the quantity x minus c is shifting by c units to the right. All right, we have one more problem where we're going to apply the summary that we just looked at. So here we have a graph of f of x. I want to graph g of x, which is f of x minus 2 minus 4 on the blank grid. We're going to begin by labeling the 5 key points, A through E, and then we're going to change each of those coordinates according to the transformations that have occurred. So my coordinates of A look like -6, 5, and B, -2, 1, C, 0, 7, D, 2, 3, and E, 4, 5. Okay, so I need to transform the x coordinate, transform the y coordinate, and give final coordinates. All right, so this is my transformation, right? F of x minus 2 minus 4. So this minus 2, we're changing the x coordinate. We're inside the parentheses, so it's changing the x coordinate. What we learned in the lesson is that when you're changing the x coordinate, it sort of goes the opposite way that it seems like it should. So that minus 2 tells me to move right 4 units, which we do by, I'm sorry, 2 units. Move right 2, which you do by adding plus 2 to the x coordinate. And then the minus 4, that's outside of the parentheses, that tells you to move down 4, which you get by doing minus 4 to the y coordinate. Okay, so to transform the x coordinate, we're going to add 2. To transform the y coordinate, we're going to subtract 4. X plus 2, y minus 4. Okay, so my x, -6 plus 2 is -4. My y is 5 minus 4 is 1. -2 plus 2 is 0. 0 plus 2 is 2. 2 plus 2 is 4, and 4 plus 2 is 6. Then I'm going to do all my y's here. So 1 minus 4 is -3. 7 minus 4 is 3. 3 minus 4 is -1. 5 minus 4 is 1. So my final coordinates are -4, 1, and 0, -3, etc. Plot all those points on my new graph here. -4, 1. 0, -3. 2, 3. 4, -1. And 6, 1. Connect them. And you get the W just like we had before, except it is shifted right 2 and down 4. All right, let's look at the domain of G and the domain of F. So the domain of F, go up to my original function F. The domain was -6 to 4, which had a length of 10. Length of 10. And then the domain of G looks like it goes -4 to 6, which was the same as the domain of f. They are the same, right? Oh, sorry, it's not the same. It was -6 to 4. Now it's -4 to 6. So the domain still has a length of 10, even though it has changed, right? So the length of the domain of f and g stays the same. All right, let's look at the range of the f and the range of g and see if their lengths change. Okay, so the range of f, that's the lowest y to the highest y. So 1 to 7 was the range of f. And then the range of g, my lowest y value to my biggest y value, is -3 to 3. So both of these have a length of 6. Okay, so the range did change, but the length did not.